and use the Kelvin equation to figure out how hard it is to dry water out of little crevices. So the question we're asking is, what's the humidity that will allow water to evaporate if it's in a crevice, a little micropore of radius 100 nanometers? Now at first, it seems like, well, what does humidity have to do with the vapor pressure? Well, it's very simple. Humidity, the percent humidity, is just equal to the partial pressure of water in the air divided by the equilibrium vapor pressure. And so if these numbers are equal, that just means that we're at 100% humidity, which means water vapor and liquid water are in equilibrium. And if this number, if the amount of water vapor in the air is anything less than the equilibrium vapor pressure, then you're at less than 100% humidity. Okay, so we know that at 100% humidity, the vapor pressure of water would be equal to this, and we won't have evaporation. If we're at anything less than 100% humidity, this number will be less than the equilibrium vapor pressure of water, and we should evaporate. So it seems like the answer is simple. Well, if it's less than 100% humidity, it's going to evaporate. We have to remember we have a curved surface here, and that means we have Laplace pressure. Now if we look at where the center of curvature is for this curve, it's outside the water, which means we have negative curvature, which means the pressure in the water is less than the pressure out here. Since the pressure is less, that's going to decrease the chemical potential of the water and make that phase more favorable. It's going to be harder to get rid of the water. And so the Kelvin equation tells us we're going to have to go to a lower humidity. So let's plug in the numbers. We know that we would have 100% humidity if we had a flat surface. That number is going to be reduced by this factor caused by the Laplace pressure. So we have to plug in all our numbers, and one of the things we have to remember is that our curvature here, since we have a hemispherical cap on either one of these ends of the micropore, the curvature for a hemispherical cap is 2 divided by r. All right, so let's plug in those numbers here. So we have first the curvature, which we said was 2 over r. So 2 over, we have 100 nanometers, so that's 10 to the negative 7th meters. We have the surface tension of water. We'll change this to SI units, 0.072 joules per meter squared. Plug in the molar volume of water. Since there's 1,000 mils in a liter and 1,000 liters in a meter cubed, this is going to be 18 times 10 negative 6 meters cubed. And then we divide by RT. So we've got 8.314 joules per mole per Kelvin. And let's see, we said 298 K, so we'll put 298 K. And I'll leave it as an exercise for you to see that all these numbers cancel, all these units cancel, because we have to have something unitless before we take the exponential. We have to be a little bit careful when we do this. The curvature here is negative 2 over r because, as I mentioned, this is a negative curvature. So that means we end up with a negative sign over here. And this comes out to 0.99, which means that being just under 100% humidity isn't enough. We actually have to reduce to 0.99 before we get any evaporation at all. In fact, if we were somewhere between 0.99% humidity and 100% humidity, say 0.995, water would actually condense instead of evaporating.